Equilibrium calculations. We have finally reached the bulk of the math in this chapter. And this will be math intensive. You're going to want to have a calculator handy as we go through this. But we're going to work through these equilibrium calculations. We're going to introduce a tool called an ICE table or an ICE chart, which will help us handle them and properly set them up. But this will really set up the backdrop for the next couple of lessons when we deal with equilibrium calculations as it applies to weak acids and bases, and then as it applies to solubility calculations as well. Now, this lesson is part of my high school chemistry playlist, and I'm releasing these lessons weekly throughout the school year. So if you want to be notified every time I post one, subscribe to the channel and click the bell notification. All right, so equilibrium calculations, and we're going to dive into doing a couple of problems pretty quickly here. But I want to cover something just reminding you of some stoichiometry implications here. So the first one we're going to look at, the first example, is going to be this reaction here, H2 gas plus Cl2 gas, giving us 2HCl gas. So all gas is involved here, and with gases we could be dealing with a Kc or a Kp, and here I've written Keq, which we're going to treat as synonymous with Kc values, as we'll see. But the big thing here is once you realize the stoichiometry here, which deals with our mole-to-mole ratios, 1 mole of H2 plus 1 mole of Cl2 gives 2 moles of HCl. It's a 1:1:2 ratio. What this means then, is that we can monitor how the concentrations change over time and relate them. So notice if over a given amount of time, I told you that 5 moles of H2 disappeared, it reacted. Well, because of the 1:1 ratio, during that same period of time, 5 moles of Cl2 would also need to disappear, also need to react. But because of the 1:1:2 ratio, during that same period of time, it wouldn't be 5 moles of HCl that would be being produced, it'd be twice as much due to the stoichiometry, and so it'd be 10 moles of HCl that would be being created. And so it is the change in the concentration or number of moles, and we'll probably deal with more with concentration or partial pressures as we'll see. But it is the changes that are related by this 1:1:2 ratio. It's not how much you start with necessarily, it's not how much is going to be present at equilibrium, it is how much they change by. That is where the stoichiometry comes into play, these mole-to-mole ratios. All right, so let's dive in and take a look at a couple of problems. And this first one here is dealing with this reaction. We got an equilibrium constant of 16. When you see a number like that, you should think, okay, this doesn't heavily favor the reactants or the products. We should have a fair amount of both present at equilibrium. So in this case, it says if 2.0 moles of both H2 and Cl2 are placed in a 2.0 liter vessel, what will be the equilibrium concentrations of H2, Cl2, and HCl? All right, so we're starting with only reactants, and if you start with only reactants, well then the reaction has to proceed in the forward direction and make some products to get to equilibrium. So just the way it works. But even if we didn't have only reactants, there's a way you can figure out which way the reaction is going to go to get to equilibrium. You can calculate your ratio of products to reactants, i.e. the reaction quotient, and then compare it to your equilibrium constant and see how that goes. So in this case, let's write our equilibrium constant expression here. And here we can see that it's the concentration of HCl squared all over the concentration of H2 times the concentration of Cl2. And notice our reaction quotient would equal the same ratio, we just wouldn't necessarily have to be at equilibrium. And so if you were doing a reaction and you want to figure out, is it going to go forward or is it going to go backward to get to equilibrium? Well, again, if you only have reactants, it has to go forward. If we only had products, it could only go backward. It's only when you have some of both that it has potential to go one way or the other. And if you wanted to be sure to know which way it was going, what you could do is just take your ratio of HCl squared over H2 times Cl2, which would be equal to Q, not necessarily K. But then compare it to your equilibrium constant of 16. If it was smaller than 16, if Q was less than K, we'd know it would need to shift to the right, which would mean the reaction would need to proceed in the forward direction. But if Q is greater than K, then it would need to shift to the left, and it would be the reverse reaction. So that would happen instead to get to equilibrium. Cool. That'll be important when we start using this tool called the ICE table or ICE chart in just a minute. All right, so in this particular problem, we are starting with 2 moles of both H2 and Cl2 in a 2-liter vessel. And this is important. So the whole idea of setting up what we're going to call an ICE chart in a minute is we're going to find out some equilibrium concentrations for all 3 of these and plug them into this expression. And so when we set up an ICE table in a minute, we're going to want to put everything into the ICE table in terms of concentrations. And technically, if you're using KCs like we are here, this KEQ is a KC, then you want concentrations. If you're using KPs, well, then you want to complete your ICE table with partial pressures. Now, technically, you can complete an ICE table with the number of moles, So, and then convert it into concentrations at the end, but that often confuses a lot of students, and a lot of students forget that last step. So I just, as a general rule, always complete these ice tables either in concentrations if I'm dealing with KCs or KQs, or with partial pressures if I'm dealing with KPs. We'll see an example of both. All right, so let's talk about this ice table for a second. So we got I, we got C, and we got E. So, and these are just a mnemonic here. So I stands for the initial concentration. We're going to have an initial concentration of all three of our species. So C is going to stand for the change in the concentration. And then E is going to stand for the equilibrium concentration. And it is the equilibrium concentrations we want to stick into this lovely formula. Because again, it's not written in, but you should remember that again, if this ratio of products to reactants is equal to KEQ, that's only true if you measure these concentrations at equilibrium. And so technically it's only what goes in this box, and this box that get entered into this expression. So if we, pick any other values at any other point in time along the way toward equilibrium, we'd be setting that ratio would equal Q, but not K. All right. So in this case, we want initial concentrations. And again, my goal is to set up the entire table with concentrations. So we're told we have 2 moles of both H2 and Cl2 in a 2-liter vessel. And the reason that's important is because you might recall that molarity equals the moles over the volume in liters. And so in our case, that would be 2 moles over 2 liters, which is going to get us an initial concentration of 1 molar for both of these. Again, you could complete this table in moles, and then everything comes out in moles. But then before you take the equilibrium number of moles and plug it into this expression, you'd have to divide by the total liters to turn it back into concentration. I prefer just to, again, put the entire table in molarities in concentrations to begin with. All right. Now, because H2 and Cl2 are mixed together, and they're the only things mixed together, we can infer that there was no HCl present initially in this reaction whatsoever. All right. So now we've got to talk about, well, how much of each of these react and how much of this gets formed. And it's the change in concentration that, again, is related through a 1:1:2 ratio here. So let's say I told you that, 0.5 molar H2 reacts. Well, then during that same period of time, 0.5 molar of Cl2 would react as well. So, but twice as much HCl would be produced. So twice times 0.5 molar would be 1 molar. And that's where this is kind of going. Now, the key is, what if it's only 0.1 molar? Well, if 0.1 molar of this reacts, then 0.1 molar of this will react as well, and you'll create 0.2 molar of this. The big deal, though, is that we don't actually know how much reacts, and therefore we don't know how much of each of these we lose and how much of this we gain. And when we encounter something like that in algebra class, we call the unknown variable often x, and that's what we're going to do here. And so here, instead of putting like minus 0.5 or minus 0.1, if I knew how much reacted, I'm just going to put minus x. And so typically your changes are going to be expressed in terms of x. Now, because of this 1:1 ratio, we're also going to lose an equal amount of Cl2, and so we're going to put minus x there as well. Now notice both of these are negative because they're reactants. We said this reaction needs to proceed to equilibrium by going to the right, which means these concentrations are going to go down, and that's why these are negative. So, but for the product, it's going to get produced, and so its change is not going to be negative, it's going to be positive. We're going to be gaining some of the HCl in this case. Cool. If the equilibrium had been going backwards to get, have we been shifting left, I really should say, the reverse reaction been spontaneous, well, then I would have been producing these guys, and I could have put plus x, and then we could have put the minus over here. So, however, it turns out, even if you just by default end up doing it backwards, you're still going to get the right answer. And so, the truth is, I usually customarily just put negative on the reactant side and positive on the product side. So, and then if it turns out it had been the other way, then when you solve for x, you would have just got the exact negative you would have gotten, and all the answers still work out perfectly. So it turns out it doesn't actually matter as far as getting the right answer. Conceptually, it should work one way or the other, but as far as getting the right answer, either way works. All right, the last part of this then is that we're not going to produce an amount x here. If I just put plus x, it's actually wrong, because again, based on the 1:1:2 ratio, I should produce twice as much of the HCl, and so it actually is going to be plus 2x. And so when you're doing the changes on an ice table or an ice chart, so minus on the reactant side, plus on the product side, and then you've got to factor in the coefficients as well. If the coefficients are just 1, then it's either just going to be minus x or plus x, depending on if it's on the reactant side or plus side, product side. But if there's a coefficient of 2, then you're going to either have minus or plus 2x. If there's a coefficient of 3, it'd be minus or plus 3x, and that's where we'll factor in these mole-to-mole ratios, the stoichiometry. All right, so then your equilibrium calculation is just the combination of what you start with plus how much it changed by to get to equilibrium. So notice this is kind of the same thing if you're driving down the road and you're doing 20 miles an hour. So and you're driving down the road doing 20 miles an hour and a cat jumps right in front of your car. And so you slam on your brakes. I was going to say accelerator, but brakes. And in this case, you slow down by 15 miles an hour. And so you were going 20 miles an hour, you've slowed down by 15 miles an hour, so how fast are you going now? Well, just 5 miles an hour. You take your initial amount, 20, plus the change of negative 15, slowing down, and leaves you at what you end at, 5 miles per hour. Well, the same thing here. You just take your initial concentration, plus how much it changed by, and then it gets you your equilibrium concentration. And so 1 plus a negative x is simply 1 minus x. Can't simplify it any further. We don't know what x is. So same thing here. 1 plus a negative x is 1 minus x. 0 plus 2x is 2x. And these are the equilibrium concentrations, all expressed in terms of a common variable x. And that's great because my big issue here with this equilibrium constant expression is we weren't actually given the equilibrium concentration of any of these three species. Don't know any of them. The goal is actually to solve for all three, but we don't know any of them. And so if you look, we can plug in 16 for the equilibrium constant itself, but with only one equation and all three of these being unknown, I can't solve for anything. But in this case, it turns out if we can write all three of them in terms of a common single variable x in this case, we will be able to solve. And so in this case, we're going to do 16 equals 2x squared. And so notice HCl concentration is 2x, and then this formula tells me I've got to square it as well. And then the H2 concentration at equilibrium is 1 minus x, and the Cl2 concentration is also 1 minus x. Cool. And now we've got a big, lovely algebraic expression to solve, which could look pretty ugly and could turn into quadratic, except we're going to cheat. So in a high school class, you are probably never going to have to use the quadratic. Now, if you take the AP high school course, you might see a solution requiring you to use the quadratic. But in a standard high school class, probably not going to be the case. In fact, for most of our college freshmen, we often avoid it for them as well. So very unlikely, but they could still ask you this question. The reason they could ask you it is we can simplify it a little bit. So I'm going to rewrite this again. 2x squared all over 1 minus x quantity squared. And so if you look at this, 1 minus x times 1 minus x, I can write it as 1 minus x squared. And the reason I've done this is if you look, you've got a perfect square in the numerator and a perfect square in the denominator, and we can actually avoid a quadratic if we realize we've got that perfect square. And what we're going to do is just take the square root of both sides of the expression. Because when you take the square root of a square, you just get the original number, 2x and 1 minus x back. And then the square root of 16 is 4. And so we're going to end up with 4 equaling 2x over 1 minus x. We'll multiply up by the 1 minus x. And so we're going to end up with 4 times 1 minus x equals 2x. We'll distribute the 4 through, and we'll get 4 minus 4x equals 2x. Add 4x to both sides. 4 equals 6x. Divide both sides by 6. And we're going to get x equals 4 over 6, or 2/3, which is the same thing as 0.67. And in this case, it has units of molarity because it's a change in concentration. Now, here's the deal. Let's say you're, going all through this process. And notice it has not been a short process. So we set up an ice table, we set up our calculation, and we get all the way to the end and we say x equals 0.67 molar. Now, had this been a multiple choice question, you might just be inclined to get all the way to the end of this and just like in an algebra class think, oh, in algebra, we're always solving for x. Well, I solved for x. There's the answer. And if your instructor is tricky enough, they would include that as one of the answers. And maybe that's an answer and maybe it's not, but this question wasn't solve for x. So typically they're saying, what are one of these equilibrium concentrations equal to? Well, it turns out none of them are actually equal to just simply x. And so if you pick an answer that's 0.67 solving for any one of these three, you're wrong. So what you've got to do is take this 0.67 and substitute back in here, here, and here to get an equilibrium concentration for all three of these. So notice 1 minus 0.67 is going to be 0.33. And that's again units molarity, same thing here. And then here we've got plus 2x. And in this case, 2/3 times 2 is 4/3, which is going to get you 1.33 1.33 or 1.34 depending if you round up and stuff. So, but those are our three equilibrium concentrations we've now gotten. So the whole point in setting up this ice chart is to write all three equilibrium concentrations in terms of a single variable x, substitute those into the equilibrium constant expression so that we can solve for x. But again, once you've solved for x, you're not done. You've got to go substitute that back into these equilibrium concentrations so that we can figure out exactly what they are. So at equilibrium, concentration of H2 is going to be 0.33 molar, concentration of Cl2 would be 0.33 molar, and the concentration of HCl would be 1.33 molar. That's how this works. All right, so our next question here is going to involve the formation of ammonia, NH3. So here's our reaction. It's given to you here on the handout. And in this case, question says N2 and H2 are mixed in a 2.0 liter vessel with initial concentrations of 3.00 molar each and undergo the above reaction. If the equilibrium concentration of N2 is 2.05 molar, what is the value of the equilibrium constant of this reaction? Okay, so now we're actually trying to solve for the equilibrium constant. This one's different. So we are not given the equilibrium constant. That's the question. What is the equilibrium constant? So once again, let's write our equilibrium constant expression to start here. And in this case, it would be the concentration of ammonia, NH3 squared, all over concentration of N2 times the concentration of H2 cubed. And again, keep in mind that all these concentrations have to be measured at equilibrium. All right, so another example of where we're going to use an ice table or ice chart. So, and again, I stands for initial concentration, C for change in concentration, E for equilibrium concentration. So, and sometimes students don't realize when they need such a chart. When is this tool useful? So, well, any kind of question you're being asked about equilibrium, obviously, where you're given both initial and, or I should say given, if you're given or asked about, or a combination of both, the initial and equilibrium concentrations of species in reaction, that's a key indication you're using one of these ice charts, or at least that an ice chart would be helpful for you. So, in this case, we're told the initial concentrations are both 3.00 molar for both N2 and H2. So we're also told that we have a 2-liter vessel, and that's a tricky part of this. We don't actually need to know anything about the size of the vessel because we already know the molarities. These were given as molarities. So notice in the last example, we were given the number of moles and the volume in liters of the container, and we had to do moles over liters to get a molarity. But in this case, we were told these were 3.00 molar solutions. We already know the molarity. And so we don't actually need that. Ooh, that's falling off my ear. We don't actually need that 2.0 liter vessel, volume at all. It is just an extra piece of information that we are not going to use in our calculation here at all. All right, so these are mixed together, and we can infer once again that if they're the only things that are mixed together, then no ammonia was in the vessel to begin with. And if we just fill in our changes, so again, if we're starting with only reactants, then this reaction has to go forward. There's no product over here that can go backward in the reverse reaction, so we can't even go backward. It has to go forward. The other way you could look at this is if you actually calculate Q and did products over reactants, but at this initial conditions, well, notice your numerator here is going to be 0, and Q is going to be 0. 0 divided by no matter what you divide it by is still 0. And so if your Q is 0, well, then it has to be less than K, because K is always positive. And so if Q is less than K, the reaction has to proceed in the forward direction. Or again, and this is common, if you realize that you only have reactants, well, then it has to go forward. But whether it goes forward or backward, though, I have a tendency of making my changes negative on the reactant side and once again positive on the product side anyways. So again, you can figure it out what it really is conceptually. So, but the truth is you'll still get the right answer either way. All right. So in this case, we're going to do minus x, but since N2 and H2 react in a 1:3 ratio, it's going to be minus 3x, 3 times as much there. Every one N2 is going to react with 3 times as many H2, so it's going to be lost in a 3 times greater quantity. And then plus 2x on the product there with a coefficient of 2. And there's our changes. And if we just do our initial plus our change, we'll get the equilibrium value. So here 3 plus a negative x is simply 3 minus x. Here, 3 plus a negative 3x is 3 minus 3x, and here 0 plus 2x is 2x. And so normal way we fill in an ice chart, except for one thing. They told us an extra piece of information. They said at equilibrium, the concentration of N2 is 2.05 molar. So we filled it in as 3 minus x, but they told us that the actual numerical value is 2.05 molar. Well, what must be true then is that 3 minus x must be equal to 2.05 molar. And so what we've done in this question is by giving you both an initial and one of the equilibrium concentrations, you can figure out X. And once you figure out X, you can plug it in for all of the changes and then get all the equilibrium concentrations. So, which is a question you could be asked, or they could take it a step further like we have in this question and said, what is the equilibrium constant? So we're going to use the information we got right here for N2, both the initial concentration and the equilibrium concentration to solve for X. We'll then plug it in here and here to get the equilibrium concentrations of the other two species, and then we'll substitute them in here to get that equilibrium constant. All right, so in this case, we've got 3 minus X equals 2.05, and I'll subtract 3 from both sides, and so here we'll get negative X equals negative 0.95, and then therefore X equals 0.95. All right, so if X equals 0.95, then we can figure out these two as well. Now, 2 times 0.95, we can probably do that in our head. So, and that's going to come out to 1.9. So, in fact, we should probably put an extra 0 on that, keep our sig figs consistent here. All right, so but 3 minus 3x here, and let me grab my calculator. All right, so 3 minus 3 times 0.95 is going to get us an equilibrium concentration of 0.15. All right, and these are all in molarity. And now that we know all 3 concentrations at equilibrium, we can now substitute them into our equilibrium constant expression. And so here, your equilibrium constant equals 1.90 squared all over. So N2 is 2.05, and H2 is 0.15, and the formula says cube it. All right, so this is where we'll take this, and we've got 1.9 squared divided by 2.05 times 0.15 cubed, and I put that entire denominator all in one big set of parentheses in my calculator, else it would divide by the first one but then multiply by the second one. And in this case, we're going to get 521.77, which I'll round to 3 sig figs based on the data we're provided to 522. Cool, there's our correct answer. And in this case, being 522, if you looked at that and I said, hey, what can you tell me about this reaction with an equilibrium constant of 522? You'd say, well, there probably are going to be more products than reactants, so, but not by a significant amount, or at least a hugely significant amount. So we wouldn't say that this reaction heavily favors the reactants or products, but that you're probably going to have a fair amount of both reactants and products present at equilibrium. And that's indeed what we see here. So we see, you know, quite a bit of this reactant, not so much of this one, and still quite a bit of this product. And just like we said, any equilibrium constant that's less than 1,000, but bigger than 0.001 should have a fair amount of both reactants and products present at equilibrium. Cool. This is equilibrium calculations, and like I said, we're going to take this as a launching point for the next couple of lessons on equilibrium calculations with weak acids and bases and equilibrium calculations with solubility equilibria as well. Now, if you found this lesson helpful, would you consider giving me a like and a share? The best thing you could do to make sure other students get to see this lesson as well. If you're looking for the study guide that goes with this lesson, if you are looking for practice problems, check out my premium course on chadsprep.com.